Hello everyone and welcome back to this online NPTEL course on aquatic geochemistry. In today's lecture we are going to start another new module, and that is of the composition of natural fresh water. In this first lecture of this module we are going to start with the precipitation composition. So, let us look into how precipitation chemistry looks like. So, by saying precipitation, we can have either the snowfall or rainfall. Okay. So, snow and rain very similar in composition. That means they are very dilute, they have very low TDS. In fact, snow will be much less having much less composition of dissolved solids as compared to rain, because the crystal structure itself does not allows the entry of a lot of pollutants inside it. But still when it falls down, when the snow is falling down, when it becomes very heavy and it falls down, that time the atmospheric dust can play a significant role. Similarly, for rain, when it is produced in the very higher levels of the atmosphere, it's very simply it's just water. As it starts falling down across that troposphere, then it gets dissolved with a lot of dust, with a lot of emissions, and it whatever gets dissolved in the water, whatever is simply reactive with water, it just gets dissolved there. So, we have some values. Okay. Rain is slightly acidic in nature and always tends to have low TDS, except where the pollutants are very high. If you are very close to a place where there is a lot of industry and there is a lot of emissions, or if you are close to a place where there is a lot of urban traffic, a lot of cars and their emissions, or if you are in a place where the where they are practicing any kind of burning event. Okay. So, it can be near to a place where there is waste incineration or agricultural waste, and they are burning the agricultural waste. So, those places are just some off the chart places. Otherwise, we know that rain will have low TDS and slightly acidic in nature. The solute content of rain is derived from therefore the dissolution of atmospheric gases and aerosols. Okay. The dissolution of gases and aerosols, whatever is there, that will dissolve. So, for instance, what is aerosol? Okay. Aerosol, these are water soluble salts in the marine atmosphere and over the coastal regions, or they can be debris from the forest fires or from the slash and burn agricultural practices, from anthropogenic emissions, any kind of emissions. Okay. So, these are remnants from any kind of burning practices, be it hydrocarbons and fossil fuels, or they can even be some of the plant exudates. Okay. So, the plants are also releasing a lot of exudates, whatever they do not require from their metabolic pathways, they are going to release it. So, all these are floating in the air itself. If you are going to filter the air, okay, if you filter this air, what you get on the filter paper, that will be calling aerosols. Okay. So, this again the filter paper, depending on the filter paper size, you can have different names given to those aerosols. Now, let us look into the chemistry and the most dominant sources of those constituents in different kinds of settings. So, for instance, when you have sodium, the marine input will definitely be very important. Okay. So, this rainfall, of course, the water has evaporated from some ocean or some sea water or somewhere. So, if it is coming from the oceanic source, the sodium will mostly be dominated by the sea salt concentrations, and therefore, will have a very high sodium. The terrestrial input will be soil. Okay. The pollution, the anthropogenic contribution come from the biomass burning. Okay. Similarly, from magnesium and potassium and calcium, the dominant sources of these ions are sea salt, the presence of higher oceanic vapor masses is going to make the concentration of these cations higher. And from the terrestrial, it can be the dust, it can be just soil and dust. From anthropogenic sources, the most significant contributor will be biomass burning, fertilizers, and for particular elements we can have particular sources. For instance, for calcium we can have cement manufacturing units, which is higher contributors. Fuel burning can be higher contributors. Okay, let us see for others. Let us see for chlorine again. So, chlorine again we have sea salt, and for terrestrial systems we do not have any significant chloride chloride coming in. And if there is some industries which is releasing any kind of HCl as gases, then we can have chlorine. So, chlorine therefore, when we are looking into weathering related studies, you will often see that we are going to correct the concentration of sodium, potassium, magnesium and calcium based on its chlorine values, because chlorine does not have a terrestrial direct input. There is no weathering input of chlorine from the normal rocks, silicatic rocks, except for halides and evaporites. Okay. Only if in the catchment you have evaporites and halides will this not work. Otherwise, what they do is we do something called a sea salt correction. What that means is, whenever we are working with some coastal data related to streams or lakes, and we are going to do weathering, then we want to separate out the weathering contribution from the rainfall contribution. Okay. Because rainfall also comes with a lot of sodium, magnesium, potassium, specifically if it is very close to the ocean, then that is very important that we do that kind of sea salt correction. Otherwise, our weathering related calculations becomes overestimated. So, what happens is that we use this chlorine as a denominator, and all the ratios of with chlorine, that is sodium is to chlorine ratio in the sea salt, and we are going to correct it with the observed aquatic system. So, if there is a river, we are going to correct the sodium bichloride ratio in the sea water and the sodium bichloride ratio in the river water, and we are going to separate out the chlorine contribution coming, the sodium contribution coming from the sea water, okay, from in the river water. Okay. So, that kind of correction is made using this chlorine as a denominator. Then there is sulphate ion. So, sulphate ion, they can again come from sea salt or from a DMS cycle. This is a particular biological decaying cycle. Okay. Then there is hydrogen sulfide from biological decay again. So, these are all the decaying release that is going to add sulphate to the atmosphere, but again it is going to be very low as compared to any other gases or any other aerosol components. Okay. Fossil fuel biomass burning similarly is going to add a lot of nitrate, ammonia and sulfates to the atmosphere. Nitrate, ammonium, they are also going to have from the natural nitrogen cycle, such as the lightning and all that. Okay. So, lightning, during lightning nitrates are getting produced due to the formation of nitrous oxides that gets dissolved in the water. Again from terrestrial sources, the nitrite that is getting decayed, they can again transform and become nitrate. And from the human pollution point of view, you can have automobile emissions and fossil fuel burning, fertilizers, everything that leads to nitrate pollution. Ammonium again a part of the nitrogen cycle. So, we have biological activity mostly, either formation, production or decay. So, since we are talking about ammonium itself, so we are going to mostly talk about the bacterial decay, that is releasing ammonium back into the system. Okay. From the human anthropogenic sources, we have ammonium, the ammonia fertilizers, and of course, any kind of waste decomposition or waste incineration practices is also going to release it into the atmosphere. Phosphates, they are mainly from biogenic sources. They can be absorbed on the sea salt, okay, and or else they can come from the soil dust. So, basically some kind of phosphate minerals which is getting into the dust. So, bicarbonate, bicarbonate is there in the air, of course. So, bicarbonate is the most easiest to understand, because carbon dissolving with water and it is going to form carbonic acid. That carbonic acid is going to again divide to H plus and HCO3 minus. So, that is how you get the HCO3, and every other element like the major elements can come from the sea salt, but if it is not, it is coming from just soil dust. Okay. So, soil dust is always present in the atmosphere, and even if you do not realize it, their volume is significant such that it alters the rainfall chemistry. Okay. And during particular types of human activities, it gets more and more intense. For instance, if there is a plant, if there is waste incineration activities, if there is any kind of land clearing, that means either they are clearing forest land or they are clearing agricultural land, then more and more soil is eroded. So, any kind of practices that makes the soil eroded, loose, and it just it is just floating in the air. So, such practices will of course increase and modify the precipitation chemistry. Then let us see how what kind of processes control its dissolved nature. This dissolved, of course, the trace metals, it depends on how they are going to be stable, right. Which particular form is going to be more stable, more mobile. So, for instance, particular elements, they are more enriched in the atmosphere as in the form of aerosols. Their presence is more because their oxides, okay, their oxide form, they have more mobility. For instance, here is a plot of different elements according to its boiling point of oxide and how much it is found enriched in the atmosphere. Okay. So, even certain heavy metals such as cadmium, mercury, they are very volatile. They are very volatile. They are volatile because of their higher volatility. They are more found in the atmosphere as compared to other molecules such as aluminum, titanium, chromium, manganese. Then there is other group of elements, zinc, lead, nickel, vanadium. Again, these are controlled by their boiling point of oxide. So, therefore, they are more of they are coming from due to their presence coming from the oxide, their stability of their oxides, they are coming from this atmospheric dust solubilization. These trace metal groups, they are just getting dissolved in the water, and if you see strong correlations between them, it is just that they are there in the atmosphere due to the moderate gaseous mobility, and when the rain is falling, they are dissolving, and you see such strong correlations between these particular trace metal groups. Okay. So, either they are derived from volcanism, or they can be released from particular biological activities, or they can be coming from sea. Okay. So, what is sea surf? Sea surf meaning when the waves are splashing. Okay. See, if you go to a coastal area, you will know that you are near to a coastal area because of the breeze. Okay. The sea breeze feels so heavy, the sea breeze feels so salty, as if you can taste the breeze, it is so salty in nature. Okay. So, from common experience you will know that the sea breeze is very heavy with all these aerosols. Okay. These aerosols, this presence of aerosols is why is it there? Because these waves, they are continuously splashing. Okay. They are continuously splashing, right? These waves, they are continuously splashing. When they are splashing, then these tiny droplets of water, they are getting mixed in the atmosphere. Okay. They are just getting released in the atmosphere, and this is continuously happening every second, every moment. More and more splashes are happening, with more and more waves. There is a continuous supply of these tiny droplets of water that is just there in the atmosphere, that is just there in the air. And if you are standing there near to the coastal ocean, you do not even have to be on the beach. You can stand in your room and you can feel the air, which is so salty. You can feel it, on your skin, you can feel it on your hair, that this air here is very different. It is very salty, it is very heavy, okay, and that is because the sea salt is having all these other compositions. Okay. So, that is what is called sea surf. That is the term that we use, that when the waves are breaking, it is releasing more and more tiny droplets into the atmosphere. Of course, the burning of fossil fuels is there, then any smelting activities of metal ores, it is releasing the dust into the atmosphere. Incineration and combustion of urban waste, huge contributor to atmospheric aerosols, and here are huge incineration factories and everything. So, a lot of urban waste, they are just burnt for the sake of getting rid of the waste. Okay. So, depending on their volatility, these metals, they mobilize and they get dissolved in the rain. Now, let us look into how the soil moisture looks like. Okay. So, from rainfall, we now look into soil moisture. Okay. That means, this is the water that is there in the interstitial layers of the soil, okay, in between the particles. So, what happened, you have to extract this water, is not flowing or readily available for you to collect, okay, but you have to extract it. You have to create a suction, you have to create a vacuum, and then you have to basically draw out this kind of soil solution. So, in high rainfall climates, where in this in this locality, if there is high rainfall, then the soil water composition, it will just resemble local precipitation, because of the very frequent rainfall events. And in these regions also, the evapotranspiration losses are very minimum because of high humidity, low temperature. So, the rainfall and the soil moisture composition very closely follows the local precipitation composition. But what happens when the soil, when the soil composition, when the rainfall is very low and it is not as frequent, then we see certain differences. Okay. We are going to observe certain differences, and that is going to be due to different kinds of processes. It can be related to direct weathering, it can be related to biological uptake and biological release, or it can be just simple due to anthropogenic activities like agriculture and all that. So, when we are looking at particular elements, so we have the study where we have a particular elements here, we have the data from the precipitation, we have moisture, soil moisture data collected from 1 meter, we have soil moisture data collected from 3 meter, and we are going to see how this two soil sample data varies and what is the net change that is relative only to the chloride as a base. So, we are going to this is different, we are going to talk about this later. So, just first let us see some values. So, the first observation is, so we have calcium, we have magnesium, we have sodium, we see this in precipitation and we see this in the soil. Okay. Now, what we do note is that the topsoil, it is dominated by sodium and nitrate. As you can see here in precipitation we have 1.4, but here we have 24 and 53. Okay. Sodium, this is 0.5, here we have 6.9 and 21. Okay. So, in soil moisture we have a significant high concentration of sodium and nitrate, and that is most likely coming from fertilizers. Okay. Most likely coming from fertilizers. What you will also note is that the TDS increases lot as we go from precipitation to soil moisture and as it goes down the soil profile. Okay. Now, what we also observe is that the calcium, okay, and the bicarbonate is simultaneously increasing many times. So, this increased from 33 times and this has increased 76 times, and that is due to weathering. This is due to weathering or due to the decaying organic interactions. So, what happens is when the organic matter gets decayed in the topsoil and this medium root zone soil, then it creates, it gives that whatever the root is responding, the carbon dioxide is coming, it gets dissolved in the water, forms bicarbonic acid, starts dissolving all the carbonates around it. So, carbonate and bicarbonate concentration gets very high. So, either it can be from the natural weathering of carbonate rocks or from the respiration of plant roots. Okay. Then there is increase in sodium, sulphate, nitrate, chlorine, they can also increase due to evapotranspiration. So, that can also lead to evapotranspiration can also lead to the increase in their components of concentration of these particular constituents. Okay. Then there is some decrease in magnesium, sodium and potassium. Why? Because these particular elements, they are very they are useful in metabolic activities. So, therefore, the plants they will uptake. Okay. So, even if there is not a decrease, what we do note is there is less increase. So, for instance, potassium, the increase is only 2.7 times as compared to other so for instance, sodium. Magnesium is only 7.3 times as compared to 33 108 values, it is just 9 as compared to 33 times of calcium. This is mainly because magnesium is uptaken much more as compared to calcium, potassium is uptaken much more as compared to sodium. Okay. So, it is this uptake that is also controlling the composition, and also there is clay formation process. As it is getting weathered, clay is also getting formed, right. So, this kind of orthogenic clay deposition also uptakes potassium and magnesium in its structure. Again, we see a huge increase in carbon dioxide, and this is from the production of carbon dioxide. So, it is just the production and uptake of different materials that you get to see. And every time what we are doing is we are seeing the net change with respect to chlorine, because chlorine is coming from the rainfall as compared to the soil. This soil chlorine is not getting produced. So, when we see with respect to chlorine, what we mean is that we are seeing the change in the system itself as opposed to addition from rainfall. It is not that any more rainfall is causing the changes, no, because we are going to correct it with chlorine, because only chlorine is coming from rainfall. So, that allows us to make changes, allows us to quantify based on this chlorine normalization. Okay. Then we get to know that what the changes are is not related to addition of more rainfall, but due to changes and processes happening in the system itself. Okay. Reactions happening in the system itself. Now, let us look into another very specific system, that is glaciers. Okay. Now, before we move into glaciers, I would like to tell you just a small introduction related to glacier hydrology that becomes easier when we talk about the system. So, glacier hydrology consists of a very well connected system, and that can be vertically connected or laterally connected. So, either you have vertical connection or you have lateral connection. Okay. And this regulates the meltwater routing, storage and export from the entire glacier meltwater body. What do we see? We have something called the ELA. Okay. So, ELA, so this can be the line of ELA. Okay. So, above this ELA we have the accumulation zone. So, above here we have the accumulation zone, and above the ELA, below the ELA we have the ablation zone. So, beyond this particular line everything is melting and getting wasted away. Okay. By meaning of wasted away means it is just getting transferred into water and either mixing with the sea or it is getting converted into rivers. Okay. Now, we have 4 kinds of systems. What we have first is the supraglacial hydrology, that is on the surface of the glacier. Okay. Now, glaciers are basically very compact ice bodies and they can be kilometers thick. They can be 1 kilometer thick or they can be 2 to 3 kilometers thick near to the poles. Okay. So, the size of the glacier is highly variable depending on the kind of glaciers that you are studying, but there are some common features that we are always observing. Okay. We are always observing some supraglacial features. So, these are supraglacial lakes that is formed due to the uneven surfaces, and these uneven surfaces they are going to collect this water, and just a formation of a lake, just like we have lakes on the land surface, we are going to have the lake on the glacier surface. Okay. So, this is meltwater generated in the summer, and this is so this water may be on top of an impermeable ice. Okay. What happens is when the lakes grow too much, they are going to again drain out. So, they are going to form some kind of cracks, and somewhere the pressure, the water pressure will force it to form cracks, and they are going to force it to join more drainage system for more networks, and it is going to get released. Okay. Finally, it will going to get released into the either ocean or to the river. Then we have englacial hydrology. Englacial means inside the glaciers. Okay. Inside the glaciers within the ice system. What do we have? We have multiple cracks, we have crevasses, we have moraines, we can have something called a vertical shaft. Okay. We are going to have some water pockets like this. So, this basically what happens is that the other region got frozen except this part. So, these are temporary pockets of meltwater. Okay. And when these get connected, when this gets connected, when the drainage network gets connected, they can supply that water and it can all come down to the main channel. So, they are just temporary store meltwater, and they can control the magnitude of the basal meltwater supply. What is basal meltwater supply? So, as the glacier is moving, okay, as the glacier is moving because of its own weight according to the topography, this layer is continuously having a friction with the land surface. The ice surface is moving on the ground. So, this is having a friction. Okay. Due to this friction, the water gets melted at that surface. So, this is called the basal meltwater. Okay. So, we have something on the ice surface. So, that is the supraglacial. We have some channels and we have a drainage network that is inside the glacier body itself. Okay. Then we have something called the subglacial, that means the basal system. So, this is the subglacial. The subglacial means inside and the bottom part. So, this is the subglacial system. So, this is the subglacial channels and all that. So, this is from the basal part, and extensive weathering is happening here, that is due to the geothermal heat and pressure melting, and a lot of solute is getting generated here. Then what we have is a proglacial drainage system, that is the downstream section. So, this is called the proglacial rivers. So, where the glacier is ending and a river is starting. So, that is what we call the proglacial region in front of the glaciers. Okay. So, we have the proglacial lakes, we can have proglacial rivers, and these can either form rivers like the river Ganga, river Brahmaputra, river Indus, they are all glacier rivers. Okay. Or it, suppose if it is in Greenland, it is going into the ocean, it is meeting the ocean. But can you see that as it is moving, we are just seeing a lot of sediments. The color is changing to more brown and it gets a lot of sediments is coming in. Okay. What it implies is that it is not just water that is flowing, it is a lot of sediments that is also getting eroded from the surface, from the basal surface, or from the debris. If it is in the areas in the continents, as you can see here, this is the Himalayan glacier, and as you can see that the ice surface, this glacier, okay, these are going to have some deposits. Okay, we are calling this moraines. Okay. So, the glaciers are always eroding the land surface, and this eroded material comes down with the drainage network. So, it is always not like this crystal blue water that you would just like to dive in. No, it is not always like this. This is a supraglacial lake in Greenland. Okay, this is not the kind of water that you see in the continental glaciers, where you are seeing a proglacial stream. This is not how a proglacial stream will look like. In fact, it would rather look like very sediment rich. So, how does the glacier chemistry looks like? And of course, here is the area of the different glaciers and the poles. So, we have Antarctic, we have Greenland, we have North America, we have the continental glaciers in the different continents, Asia, Europe, South America, in Australasia and Africa, and what is their present volume, okay, and how much the sea level will rise if these gets melted. If so much volume gets melted, how much will the sea level rise, given the entire gets converted just simply into water. So, what do we see is that these glaciers, their major ion, it is a huge, they are very concentrated, they have very high calcium, magnesium, sodium, potassium, bicarbonate, sulphate, chloride, very high values, and in fact, bicarbonate will be very high, sulphate will be very high, chloride depending on whether there is evaporite, halides, whether there is some influence of rainfall or not, otherwise it will be low. Other things, calcium, magnesium, sodium, potassium, they are dominated by rock weathering. Okay, they are always dominated by rock weathering. Just look at Canadian high Arctic, so high values, Himalayas very high values are also there. Okay. So, these kind of water, okay, glacier meltwater is also having high concentration of dissolved anions. Okay. Dissolved ions, why? What kind of weathering is going on? Okay. So, in the subglacial environment, okay, that is occurring at the ice bed interface, there are lot of physical erosion. This physical erosion continuously produces fresh reactive mineral surfaces. Fresh reactive mineral surfaces, that means the minerals they are getting broken and they are just having more and more dislocations and breaks where the atoms can get more reactive. Okay. So, the chemical reactions are controlled by the high surface area. Okay. More and more surface area is available for the reaction. The short water rock contact times, the contact time is low, but the high surface area and the more reactive nature makes the contact very significant. And there is a spatial heterogeneity in hydrology and redox. What kind of spatial heterogeneity? For instance, here we see that this is having more anoxic regions. Okay. These are more anoxic regions. As soon as it goes here, these are more oxic regions. Similarly, vertically also this is more oxic, but inside these pockets these are more anoxic regions. So, vertically and laterally there are pockets of oxic, pockets of different redox spatial heterogeneity is there, and this is because either there is a distributed system, distributed meaning that the flow is separated, it is distributed differently. So, there is just some water filled fractures, some pockets. What is the other way? The other way is the channelized system. That means, all these distributed water bodies now gets channelized into one channel and then they can get released. And the distributed systems, they remain separate for longer residence time, it is like a separate anoxic niche. While the channelized system is a much fast flowing and oxic, the solutes are getting continuously flushed. So, even though the subglacial zones are remaining hidden, they are very efficient geochemical reactors, they are like a bed of reaction, and even there is a freezing temperature. The freezing temperature does not hinder the kind of reaction that is happening. It is the surface area, it is the fresh reactive mineral surfaces that is going to control these the production of more solutes. What kind of weathering therefore is happening? Either we can have carbonate dissolution. Okay, so, the primarily all the carbon magnesium bicarbonate is going in, or there is sulfide oxidation. Okay, that means to balance the acidity, okay, to balance this acidity, carbonates are getting dissolved. Okay. So, we have such kind of reactions with pyrites. So, it just depends on the geology of the area. If the area has more kind of pyrites, sulfides and all, they are getting oxidized, and of course, some kind of buffer will always be there and these reactions will follow. So, we have not only calcium magnesium rich water, we also have sulphate rich water, and there is enrichment of all other metals that comes with the different kinds of rock types. And of course, there is silicate weathering that is always happening there. So, silicate weathering, this is the most basic equation of silicate weathering, where anorthite is getting weathered into a clay mineral, and this is the reaction that is going to contribute to the long term carbon dioxide consumption, Okay. So, this is the dominant weathering reactions that is happening in the glaciated terrains. Therefore, we have redox zones, that is oxic zone and oxic zones. we have the sulfate reduction happening, we have FeMN reduction happening, we have methanogenesis happening, we have different kinds of oxidation going on, cycling, elemental cycling going on. So, even though it looks like that the subglacial environment is inert and nothing is looks like happening, it is biogeochemically very active. Similarly, the proglacial zone is very different. Okay. Here it is the more oxic, very long residence time, oxygen is available, there is seasonal warming is going on, there is more development of soil, biofilms and vegetation. So, therefore, we see the formation of FeL hydroxides, clay is getting formed, some other metals can get deposited, it can get settled down with the organic matter or with the other clay minerals. So, in the subglacial zones, the solutes are getting generated. In the proglacial zones, they are either getting filtered, they are transforming, and this proglacial zone, this controls how these solutes are getting exported in the downstream region. So, understanding glacial system needs a lot of a lot of samples, different zones, and we need to very well understand how the chemical reactions are happening, how it is getting modulated in the downstream reaches. So, at no point of time I think you should be thinking that when we mean glacier meltwater, the glacier meltwater is going to look like this. Okay, it is a very morphed idea with such kind of pictures, because this is just the surface of certain areas which are debris free. Most of the glaciers in our Himalayan regions, we have a lot of debris cover. So, therefore, the water in these kind of proglacial streams are extremely rich in solutes. Okay. So, with this I will come and end to this lecture, and we are going to discuss other systems in our next lecture. Thank you.